right, so let's go ahead and review what we were planning to talk about. So what we said is that we're trying to make a control system in this particular lab. And what we're trying to do is control a DC motor. And we talked about the basic ideas behind the DC motor. We said essentially what we do is we try to create a magnetic field. Like in this case, what I would have is a magnetic field going from north to south. Okay, so that would be the B field. There'd be a current going through that wire like that. And there'd be a force on that wire, the magnitude of which we said is IL cross B, right? It's the magnitude of the force. The direction of that force, we do the right-hand rule, we'd see that the wire would jump up. Okay? Now, that's the same basic principle that we utilize in a motor. And so what we said is, in this case, so this picture, basically, I create a B field that rotates around. Okay, so the B field rotates around. In this case, the B field is created by a current here. That B field jumps across like this. All right, so I get my B field jumping across. Remember I said last time when I showed you this, that gap is really tiny, right? So B field circulates around in a clockwise direction, and then basically what it does is it jumps through across the air gap and into the rotor, okay? And then flows through the rotor. So the idea here is that I use iron or something that guides the flux well. Remember I talked about that in lab 1. I want to guide the flux to where I need it to be. In this case, I needed to be in that air gap. So we did the right-hand rule last time, and we said, okay, there's going to be a force on these wires. So if I have a current up on the top side of this guy that's coming out of the wires, there's going to be forces like this, right, in a clockwise direction like that. Okay? So this guy's going to move clockwise. And ultimately, we determined the torque on this thing. And we said torque, actually, I'm not going to write it like that. I'm going to say torque is, we basically had a constant, Km, that we called the motor constant, that depends on geometry and things like that, number of turns. That torque is equal to Km times Ia. We also had that the voltage out of this thing was equal to, I should be careful. This guy produced an open circuit voltage, V equals Km times his speed. All right, and I said those are the two critical relationships that I have in any DC motor. Okay, voltage equals K times omega, torque equals K times Ia. So in other words, more current means more torque, more voltage means more speed. Okay, now let's get out of there real quick and let's start talking about this a little bit more. So last time what I started talking about with you guys was basically how do I take that and convert it to a circuit model. So what we said is this motor can be like a generator. If it's a generator, it means if I spin it. So remember, if I put that thing on a drill, right? And I said I had this open circuit voltage that I measure at the terminals, VA. Okay. In other words, what I do is I make a circuit model for this motor that looks like this. So I have a voltage that I apply at the terminals of it. A current would flow in. And what I have inside here is the resistance. That's just the resistance of the wires and things like that. And then I have this voltage source Km times omega. And this guy represents the electromechanical energy conversion that happens. And so when I call this the open circuit voltage, let's say I was operating this guy as a generator and it was moving at a particular speed. Well, then I would measure a voltage here at these terminals when there's no load connected. I would measure a voltage at the VA terminals. That would be Km times omega. Okay? And so remember how we got this, right? I said if this was an ideal transformer, then I would have hey, sorry for that abrupt change. I thought I had done something wrong there, but I think I got it all worked out. Okay, so I said this thing's like an ideal transformer. Okay, it's an electromechanical transformer. So I have energy at the primary and energy at the secondary. In this case, the primary would be these terminals, the electrical terminals, and the secondary would be the mechanical port where I have a particular torque and a particular speed. And what I said was power electrical has to equal power mechanical, meaning that VA IA has to equal torque times omega. All right, and this is the basic idea that I utilize with this thing. All right, we said if I plug in the torque is KIA, IA's cancel, and that's where I got the VA equals Km omega. Now, again, this is the open circuit voltage. In other words, it's the voltage I would measure if this guy was a generator operating at no load. This source in here, sometimes I call a back EMF or electromotive force. Okay? All right, but I've got my basic circuit model in place. All right, so critical things, torque equals Km IA, voltage, back EMF equals Km omega. More speed, more voltage. More current, more torque. Okay? All right, so I've got my circuit model, but that's not the whole model of this thing, right? The whole model has to include how there's some conversion between electromechanical energy or electrical energy and mechanical energy. And I need to put all that together. All right, so before I talk about that completely, what I want to do is I want to talk a little bit more about the problem that we said we had at the beginning of this. Right, I said I wanted to make a control system, and I wanted to make the motor go faster or slower based on some kind of a command. All right, so what we kind of talked about was, I said, all right, in a control system, what I have to have is a command, some sort of what I would call a decision unit. All right, I have a power amp. All right, power amplifier, because I need obviously both voltage and current to get torque, right? Because of that relationship between current and torque, I need power. I need to get a lot of current. All right, so then I have my motor, and then I have the speed of the motor and a speed sensor. All right. So basically what I do is I have this decision unit takes my command, and it takes the actual measured speed from the sensor, decides what to do, whether I slow the motor, slow the motor down or make it go faster. All right. So this decision unit basically provides its decision to the power amplifier, which makes sure that we have enough current and voltage to drive the motor to the right speed. All right. What we said is I make use of negative feedback. And what that means with negative feedback, we said, is that if this thing needs to speed up, then what I do is I apply more voltage. If it needs to slow down, I apply less voltage. So with negative feedback, what I do is if I basically respond to a change. If I slow down, I act to speed up. If I speed up, I act to slow down. That's the basic idea of negative feedback. It always tries to restore where I was before. So what we said is, I can kind of model this whole thing. Typically, what I do is I have something like this. that decision unit typically is some form of, let's say, subtraction. Okay. So I have my command. I might put a voltage in here for my command. And then I have some sort of a feedback signal. So let's say my sensor has a gain. I'll call it KS. All right. So this is, let's say this is the power amp. And let's say this is the motor. Okay. Here's a block diagram model of that control system. So what I do is, this would be the voltage VA at the motor terminals. All right, so what I do is I take this command voltage, take the difference between that and the speed of the motor, and I ultimately create a command out of the power amplifier that drives the motor. And I showed last time, I'm not going to go through it now, but I can create a transfer function of that whole thing, right? It basically looks like this. H of S, H M of S times KS. Sorry. Looks like this. Okay. All right, that's not hard to show. I'm not gonna, like I said, I went through that in class last time. I'm not gonna go through that again, but not hard to show. What we said last time basically is that if H of S is really big, so if H of S is much, much greater than 1, then this whole thing becomes such that V command is approximately equal to Ks omega. In other words, the signal that comes out of the sensor, right? That's the ideal situation, and that's what we want to create, okay? Now notice what we do here is these are transfer functions, right? And you guys kind of know this. Transfer functions we like because they're input-output models, okay? When I say input-output models, essentially what that means is I have an input and an output, right? And I can make nice use of a model that I can design with, all right? Power amplifier we can kind of handle. You guys have seen power amplifiers. You get the idea of the power amplifier. That's not too hard to wrap your head around. A little harder to wrap your head around perhaps is the motor, all right? Because we don't have a dynamic model of that. When I say dynamic model, right? So dynamic model means it captures the dynamics of the system, okay? So in other words, if there's capacitors and things like that, right? It captures sort of the energy storage effect of those things, okay? So like for instance, when I say dynamic model, I want a model that captures the input-output relationship between the input and output, I guess. So V in, R, C, V out. Imagine if I had an RC circuit like that, okay? So in that type of thing, what I say is that I can come up with a dynamic relationship, right? And what that dynamic relationship does is that dynamic relationship describes how quickly the system responds to a particular input. In other words, it doesn't just tell me what happens in steady state, it tells me what the overall response is. So in other words, like for this RC circuit, it would tell me, okay, if I put a step into the system, what would the output look like? Well, if V in was a step function, V out would be an exponential. Now, why is V out an exponential? Well, it's an exponential because I need to get energy. It takes time to load energy into this capacitor. right? Energy can never change instantaneously. And because energy can never change instantaneously, it takes time for the voltage on the capacitor to build up. And eventually, let's say I put a step of magnitude V, eventually I'm going to have 1/2 CV squared stored on that capacitor. And it takes time for the energy to go from 0 to 1/2 CV squared. All right, and the RC time constant dictates how long that takes. Now, one way to capture that dynamic relationship is to make use of differential equations. That's actually the most straightforward way to do it, right? Where basically I say V in equals IR plus V out. But we know that I in the capacitor is C dV dt, so this becomes RC dV out by dt plus V out. Now, what I can do is, so this is a relationship that is an input-output relationship, right? The input is V in, the output is V out. I can solve for a given input, right? But we all know that solving that's a pain. Nobody really wants to do it. So the alternative with this, one thing I can do, you guys know that I can use impedance to get to a transfer function. But an equivalent thing would actually be to make use of what we call a Laplace transform, which I think you guys should remember. So V in of S is the transform of V in, whatever V in is. And over here on the right side, what do I get? Well, the transform of V out is V out. That's pretty easy. When I take the derivative of a function, you guys all should have taken this in signals and systems or in calculus somewhere, right? The Laplace transform of the derivative of a function, what do? I multiply by S. So what I get is S RC V out of S, like that. If I rearrange this whole thing, I get V out of S equals 1 over S RC plus 1 times V in of S. Okay? That is, this guy right here is the transfer function of this thing. And so what I have is a transfer function model. And this, remember, is the same model I would get if I used impedance analysis. Okay? What we see, when we did impedance analysis, if you remember, our basic assumption was that we had sinusoidal inputs. All right? In this case, I'm going a little bit more general, and I'm saying, all right, imagine I can have any type of input. If I can have any type of input, I use the Laplace transform to be able to describe that. So when I say any type of input, in other words, I mean I can have a step function or a ramp function or whatever else. And those are the types of things that we often come across in controls. Okay? Now, so let's just understand this. What I want for controls, maybe what I need for control is, one, a dynamic model. And I want that model to be as simple as possible. So the way what I do is I use the Laplace transform. Okay. The Laplace transform gives me a simple multiplicative input-output relationship like this. In other words, this is a multiplicative relationship. This is a differential equation relationship above it, right? I can get one from the other, and I prefer to have this sort of a simple thing. Now I'm saying I need a dynamic model for control. Why do I need a dynamic model for control? Well, let me go back to this picture up top of my control system. All right? So we know that what we want to have happen is we want V command here and this sensor output here. We want those two values to become equal, so the difference between them is 0, right? We said that's the ideal thing. That means my system's following me well. But let's say, for instance, that the speed drops. What we know is supposed to happen is that the speed drops the sensor value drops. And so the difference between the command and the sensor value is going to go up, and the motor is going to speed up a little bit. Now, the question is, let's say the motor does slow down. How long does it take for this process to sort of occur? In other words, how long does it take for the negative feedback to act to get the speed back up? Well, that all depends on what h of s and hm of s is. In other words, it depends on the dynamics of the process, right? If that process is really fast, what could possibly happen? Well, possibly the speed could drop, the sensor voltage drops, this value goes up, this value goes up. The speed possibly could overshoot. Let's say the speed overshoots, so that all of a sudden the sensor output goes above the command, right? The sensor output goes above the command, I could really start to now cause the motor to try to slow down again. So what could happen possibly is if I looked at the speed as a function of time, I might see the speed doing this, right? In other words, it might oscillate. I might try too hard to overcompensate. And in the process of trying so hard, what I do is I force the thing to never really get to a steady value, okay? If I wanted this thing going at, let's say this guy was centered about, 100 RPM, right? If I'm centered around 100 RPM, I might start spinning around that, going between, who knows, between 110 RPM and 90 RPM. But if I know the dynamics of the system, I can make it so that it stays flat, okay? That's what I want to have happen, that it follows my command both well in a steady state sense. So in other words, V command and V sensor output equal each other. But it's also the case that I don't oscillate around that point. This would be what I call unstable, okay? So in other words, this guy has got an instability. In other words, he can't actually settle into the right condition. Okay, so it's basic idea with this is I need to have that dynamic model to be able to understand exactly how to deal with the control aspects. So the question then becomes, how do I look back at this motor and come up with a dynamic relationship for this motor? Okay. All right, so let's look at that. How do I get a dynamic relationship for the motor? Motor dynamic model. Okay. So to begin with that, the way I look at this is I say, well, the motor has energy storage. In other words, the motor stores energy just like this RC circuit does. In case of the RC circuit, my input is a voltage at the input. Right, my output is a voltage, but effectively what I'm doing is I'm storing energy in that capacitance when I apply a voltage, right? Well, the same thing happens with the motor. If I apply a voltage at the motor terminals, right? If there's a voltage VA that I apply at the motor terminals, current flows in and I store energy there. Where I store energy is actually in the mass, the rotating mass, okay? Think about that for a second, right? If I speed up a motor, I apply a voltage, the motor speeds up. If I try to slow the motor down, in other words, I stop applying a voltage, the motor doesn't slow down right away, right? That's because there's energy stored in that rotating mass, right? Think about a car. All right, so here's a really ugly car going down the road at a particular speed. That car stores an energy 1/2 mv squared, okay? Just like I have 1/2 CV squared here for the capacitor, I have 1/2 mv squared for the energy stored in that moving mass. If I let go of the gas, right, the car doesn't instantaneously stop because there's energy stored in the mass of that car, and that energy needs to slowly go away. And so if I looked at what the speed of the car would do, is it would sort of exponentially fall off. And boy, that looks a lot like the discharge of an RC circuit. So I must be able to come up with some kind of a dynamic model, just like I do for the RC circuit, that represents this effect of energy storage. Okay, so let's think about how we would do that here. In other words, I need to get to some dynamic model. It's not clear how I can use impedance or anything like that with a motor to do that, because I need to talk about electrical and mechanical things. But I can get to a dynamic model by using the Laplace transform. I can write a differential equation and then convert that differential equation over to the Laplace domain to get myself a transfer function. All right, so how do I do that? Let's try it. So for the motor, what are the critical relationships I have? So for the motor, I know that I have, here's VA, IA, RA, KM, omega, is that voltage right here, okay? That represents the electrical side of the system. So in other words, if I apply, let's say I'm going to apply a voltage source to this guy, okay? I want to know what's going to happen to the speed. I want to know what the speed is going to end up doing. Well, I know that torque equals Km IA, and I have my vac EMF voltage here is Km omega. So this is the torque. This guy here is the torque that the machine produces electrically. Let's say what I did. So let's say I had a motor. So here's VA. And let's say that that motor is connected to, I don't know, a fan. Okay. So what's going to happen? If I apply a voltage to this thing, a current's going to go in, and it's going to try to spin this guy in a particular direction. But if I take a fan blade and I spin it through the air, what's going to happen? I know that there's going to be a friction force that tries to slow that thing down, right? If I try to move anything, right? If I move a car down the road, right, there's a force of friction, both from the road, but also there's a force from the air as I try to move through the air. Same thing happens with fan blades, right? If I try to move this fan at a particular speed, right, it takes an electrical torque to make this guy move, and there is some sort of mechanical load torque that fights back against this. There's an electrical torque that causes it to move forward, a mechanical torque that causes it to slow down. All right. What happens is, in steady state, those two torques should become equal to each other. Okay. Now think about that for a second. Think about pushing. If I was actually there in class, I'll do this for you next time. What I do is I push a chair along the floor, right? Once I'm pushing the chair and I'm in steady state, right? I can move at a steady state, and the force of friction and the force I apply to move the chair are the same. Okay, so in other words, what I want to do is I need to capture the two things that are happening. Capturing the fact that I'm putting electrical energy in here, and then capture the fact that at the fan blades over here, what I have is I have a torque produced by the machine and a mechanical torque that acts to try to slow this thing down. All right. All right. How do I do that? The electrical side is easy. On the mechanical side, okay, we get this sort of electrical mechanical torque idea a little bit, but how do I use it? To do that, I have to go back to Newton's second law. Okay? Newton's second law is the one that says force equals m times a. The net force on an object is equal to mass times acceleration, or m times dv by dt. So I'm pushing a block. Oh wow. It's a really funny looking man, but let's say this man is pushing, so F push, pushes the block M along a surface. There's a friction force pushing back against him. The net force on this guy, F net, is equal to F push minus F frick. Okay. In steady state, so steady state, the meaning of steady state is constant speed meaning dv by dt is equal to 0. So in other words, I'm not accelerating. So that means that F net must be 0. In other words, the force that I am pushing with is exactly equaling the friction force. All right? I have the same relationship in a rotational system. So in a rotational system, what I say is the net torque is equal to the torque that pushes. In this case, the torque that pushes is the electrical torque produced by the machine. The force of friction is the mechanical torque. All right, let me try to be consistent with what I said before here. So this is the push, and this is the friction idea. All right, those two things have to equal to, in this case, what we say is J d omega dt. What is this? This is moment of inertia, which if you remember from physics is like a rotational equivalent of mass. And this is angular acceleration. All right. So I have this basic relationship, Newton's second law rotationally. Now, what are all of these things? Okay, the mechanical friction is usually a little bit tricky, right? Mechanical friction, who knows exactly? That guy depends a little bit somehow on speed, typically, right? The faster I'm going, usually friction depends usually on how fast I'm going. I'm not going to deal with that. That's a little bit more complicated than I want to get into right now. But the electrical torque is this guy, T elec. The electrical torque is the torque produced by the machine. That's the torque that's proportional to current. So what I can do is I can say that this whole relationship becomes Km IA minus the mechanical torque equals J times d omega dt. So again, in steady state, omega is constant, speed is constant. In this case, rotational speed is constant. So what that means is d omega dt is 0. This thing's not accelerating, it's moving at a constant speed, so it means that kmia and T mechanical are equal to each other. So in other words, motor produces exactly the torque needed, exactly the torque needed to move at constant speed. Okay? That's the basic idea. All right, and this torque mechanical would be sort of my friction that I talked about. And you can kind of make some sense of that if I had something like my funny looking fan blades up there. All right, so how do I deal with that to get to my dynamic model? That's what I really wanted to. So this is a dynamic model. It's just a dynamic model that deals with, in this case, deals with differential equations. But I don't like differential equations. I'd rather get this to some form of a differential equation model. Okay, some form of a differential equation model. And there is a way to do that, right? How can I do that? Well, it's not too bad, right? What I can effectively do is convert this guy into a transfer function using the Laplace transform. So if I do the Laplace transform, I get Km IA of S minus T mechanical of S equals J S omega of S, like that. All right. So I have that basic relationship. Okay. And so I can look at this like so. Looks like what I have is two separate inputs. One input is this current. One input is this mechanical torque. So this is a linear system. If I have an LTI system, I can use superposition. Okay. So let's say T mech equals 0. So let's say the mechanical torque equals 0. If the mechanical torque equals 0, I have Km IA of S equals Js omega of S. Okay. Now that's getting pretty close to a transfer function I can make use of, but I have a little bit of a problem because I don't know exactly what IA is. I am applying a voltage at these terminals. Okay. But if I look at this circuit, right, I can see that VA of S minus Km omega of S has to equal IA of S RA. In other words, what I just did here is Ohm's law, right? Or, well, I guess what I really did was KVL for that circuit, right? So let's combine that here. So I have from KVL VA of S minus Km omega of S equals IA of S times RA. Okay. So effectively what I see is that IA of S has to be equal to VA of S minus Km omega of S all divided by RA. So what do? I take that and put it over into here. Okay. If I do that, what I end up with is that omega of S over VA of S, the transfer function I get for the motor, equals Km. Well, let me not skip steps. I was trying to skip steps, but let me not do that. I think we'll all just get ourselves confused if I do that. Okay. All right. So I have, once I put that in here, right, I have Km VA minus Km omega. I'm going to remove the of S's. Js omega. In other words, I just plugged in this IA result into the top equation. Okay. Now, what do I have to do? Well, I have to rearrange things. So let's rearrange this guy a little bit. And let's say I've got Km over RA times VA equals omega times JS plus Km squared over RA. All right. So I just sort of rearranged that guy a little bit. So that means ultimately that omega over VA equals Km over RA JS plus Km squared over RA. So in other words, this is getting to be my transfer function. So omega over VA, let's rearrange this guy. If he's a transfer function, I like him to be in the form like this, right, where I've got poles and zeros and such. So in this case, I'm going to rearrange this guy so that he looks like this. Right? So what I did was I factored out a Km squared over RA on the bottom. Okay. So when I do that, the RA's cancel, Km's cancel, and I get this 1 over Km divided by S tau plus 1, where my tau is JRA over Km squared. So let's step back and think about that result for a minute. What that says is that the motor has one pole. Looking at that, I have a constant over S tau plus 1, just like I have if I look at an RC circuit. An RC circuit has a transfer function that's a constant over S tau plus 1. That means that the motor is just like a low-pass filter, right? In other words, what do I mean by that? I say the motor is just like a low-pass filter. To say that the motor is just like a low-pass filter effectively means the following, right? Effectively what it means is that if I apply a step in voltage into the motor, it's going to reach a constant speed, and what its speed is going to do is do that. So in other words, if VA were to be a step function, the speed would slowly build to a constant value, right? That's what this says. It also says that even though this is a DC motor, what it says is if I apply a low frequency voltage to this thing, what I see is that low frequency sinusoidal voltage would cause a low frequency, would cause a variation in the output. In other words, a sine wave at the input would be a sine wave at the output, but only at low frequencies. In other words, this guy looks like some kind of a low pass filter. Okay? He looks like some kind of a low pass filter. Now, it's kind of an interesting sort of basic idea to this thing, all right, is that he's a low pass filter. Now, why do I care about that, right? What I've learned is basically two things. I now have a dynamic model for the motor, right? What that dynamic model tells me is what this time constant is, right? That time constant tells me about the cutoff frequency of the low pass filter, but it also tells me how quickly it takes, or how long it takes for the speed to respond to a change in input voltage. So if I have a step change in voltage, let's say by 1 volt at the input, how long does it take me to get to my new speed? Well, I see it right here, right? The time constant tau tells me that. So if the moment of inertia is bigger, if I have a big fat machine, so J is big, right, it takes longer to get to that final speed, right? If RA is bigger, it takes me longer to get to that final speed, right? So that's kind of the important relationship there. Now, how do I make use of that? Well, I make use of that in kind of an interesting way. Ultimately, first of all, this is my HM of S. And it is the missing link that I will bring back into this guy right here. Right? It'll allow me to complete that dynamic model. However, what it also tells me is something interesting. Right? It tells me that if I have my motor, in this case, the output is a speed. The output is something mechanical. The input is something electrical. Right? What it tells me is, let's assume that I put in something for VA that looked like this. Okay? So let's say it's periodic with a period D. All right, and let's say it's high for half the period and low for half the period, and it just repeats. This is 2T, etc. Let's say this was my VA. Okay, you guys know that by Fourier, right, what this looks like is it's a DC component plus a component at T, well, let's say it this way, plus a frequency component at 1 over T. Right. That's my fundamental. Then 1 at 3 times that fundamental. 1 at 5 times that, etc. Right? We talked about that all the way back into lab 1. All right, now that says I can model the input, we said, as some value. In this case, it would be 0.5 times, let's say this was a voltage V, 0.5 V, plus there'd be some V1 sine 2 pi ft, right? And then there'd be a whole bunch more, right? Well, what this says is if I take that voltage, hook it up to the motor, so this is my motor. If I take this voltage and hook it up to the motor, if it's the case that my pole frequency, if that frequency is much, much lower than the frequency of this guy, the frequency of my input, if that 1 over tau is much, much lower than the frequency of my input, then it becomes the case that we do not, so if this is true, we don't see components at 1 over T, 3 over T, 5 over T, etc., etc. All those components go to 0. In other words, they produce no effect at the output. So to call the motor a low-pass filter effectively says that if I put in an AC input, right, and if that AC input has a frequency that is much, much greater than the pole frequency, there is no output. Okay? If the pole, so if the frequency of the input is much, much greater than the pole, there is 0 output. So in this particular case, the only component that provides me with a response is 1 at DC. These guys all have 0 effect. Now, what's useful about that is that it ultimately allows me to create a voltage that's variable at the input to the motor in a really, really simple way. Okay? How? Well, basically using the same idea that we talked about back in lab 1, right? back in lab 1, we showed this picture where we took two MOSFETs and this DC voltage source, and we turned the MOSFETs Q1 and Q4 on and off very, very rapidly, right? We use this same principle. In this case, what I do is I say, I change the duty ratio of this waveform here. In other words, I change how long the top MOSFET is turned on, right? This MOSFET is on for a time t equal to dt in each cycle. Okay, that's really important. What that ultimately tells me is, as you guys know, MOSFETs running in this region of operation are lossless. What it says is control of the speed. Control of speed requires control of the DC voltage, which is controlled by dt, right? This is easy to do with a microcontroller. In other words, microcontrollers can very easily handle timing, right? They run with a clock. And because they run with a clock, they can easily control this amount of time dt. And so this technique of driving the motor in this method is called pulse width modulation, or PWM. So what I do is I vary the DC component of the voltage here. And so if I hooked my motor up, what would I do? I'd hook my motor up here. My motor would go here. Right? So V out across the switch would basically be VA for my motor. And in this case, it's not hard to show that the DC component, so V out DC, is the average of V out. Sorry, I don't know why it's doing that. V out. That is not hard to show, is D times, in this case, VDC. Okay? So as the duty ratio, what I call the duty ratio, or the fraction of time that the top switch is on, that duty ratio controls the DC value. This is why microcontrollers always have what we call PWM modules. And it's kind of the jumping off point for us to begin to talk about how microcontrollers are useful to being able to provide this motor control functionality. Okay? All right, and we'll leave it there.